Before space stretched wide, before time took its first step, before even emptiness existed, there was nothing. No light or darkness, no here or there. Yet somehow, from that absolute nothingness, an entire universe exploded into being, filled with stars, galaxies, and eventually, us. But what is nothing? Is it an empty void waiting to be filled? Or a hidden realm where the rules of nature twist into something unimaginable? Did the universe burst into existence on its own? Was it triggered by a force we haven't discovered? Or something beyond science entirely? How can everything, space, time, matter, life, emerge from a place where nothing existed to begin with? If you like the content, consider liking and subscribing to the channel, as tonight we dive into the moment reality switched on and explore the strange physics that may reveal how the universe created itself. Get ready as we start. The first step of unraveling the mystery about universe's creation is by understanding about particle physics. Particle physics is a type of science that looks at the world of really tiny things. It studies the basic particles that build our universe and the powers that make them work together. Unlike the everyday things we see, which follow normal physics rules, the world of supersmall particles follows different rules called quantum mechanics. This world is both amazing and strange. The main goal of particle physics is figuring out what the universe is built from and how it works at the deepest level. Scientists in this area study particles like quarks, electrons, and neutrinos. These are the building blocks of atoms, which themselves are the building blocks of everything. These particles are incredibly tiny, so tiny that how they act challenges what we normally think about space and time. One major win in particle physics was creating the Standard Model. This is a theory that explains the basic forces, except gravity, and particles that make up the universe. The Standard Model says there are four basic forces: the electromagnetic force, which creates electric and magnetic effects; the weak nuclear force, which causes radioactive breakdown; the strong nuclear force, which holds quarks together inside atoms; and gravity, which isn't fully explained by this model but controls how masses pull on each other. The Standard Model has been really good at predicting and explaining how particles act in countless tests. But it's not the final answer. Scientists are still looking for a better theory that can include gravity and explain the mysteries of dark matter and dark energy. These make up most of the universe's stuff and energy, but we can't directly detect them. Studying particle physics needs really advanced technology like particle smashers and detectors. These machines speed up particles to almost light speed and then crash them together. This lets researchers watch what happens and see what new particles get made. The Large Hadron Collider, LHC, near Geneva, Switzerland, is one of the strongest particle smashers in the world. This is where scientists found the Higgs boson in 2012, a particle the Standard Model predicted that gives other particles their weight. Finding this was a huge step forward, filling an important gap in what we know about particle physics. Even with all its complexity, particle physics is driven by one simple but deep question: what is the universe made of? Trying to answer this has led to amazing discoveries and new technology, including the World Wide Web. The web was first made at CERN, the European Organization for Nuclear Research, to help scientists share information. As we look deeper into the mysteries of the universe, we see an interesting connection between space science and particle physics. This connection creates a complex pattern that covers both the huge size of space and the tiny world of subatomic particles. Cosmology studies how the universe started, what it's made of, and how it changes. It finds a surprising partner in particle physics, which focuses on the basic pieces of matter and the forces controlling them. This teamwork opens new ways to understand not just what the universe is made of, but also how it started and grew over billions of years. At the center of this connection is the Big Bang theory, a key idea in cosmology. It says the universe started from an incredibly hot, packed state about 13.8 billion years ago and has been getting bigger ever since. Particle physics helps us understand this first moment by looking at how particles act at super high energies. These are like the energies that existed just tiny fractions of a second after the Big Bang. The conditions of the early universe are recreated on a small scale inside huge particle smashers like the Large Hadron Collider. This lets scientists study reactions that happened when the universe was brand new. One really interesting part of this connection is exploring dark matter and dark energy. These mysterious things together make up about 95% of the universe's total stuff and energy. Dark matter is thought to be made of particles that don't take in, bounce back, or give off light. This makes them invisible, and we can only detect them through how their gravity affects things. Dark energy is believed to cause the universe to expand faster and faster. Particle scientists are hunting for particles that could be dark matter. They use detectors underground and in space to look for signs of these hard-to-find particles. Meanwhile, space scientists use what they find to build better models of how the universe is put together and moves. Also, studying cosmic microwave background radiation leftover from the Big Bang shows a great example of how cosmology and particle physics meet. This radiation gives us a picture of the universe when it was just 380,000 years old, before stars and galaxies formed. By studying its small temperature differences, scientists learn about how matter was spread out and what the early universe was like. This helps theories in both cosmology and particle physics about the basic forces and particles at work when the universe formed. This approach that combines different fields doesn't just help us understand the universe better, it also challenges and improves the theories in both areas. For example, differences in measurements of the Hubble constant, which tells us how fast the universe is expanding, suggest there might be new physics we don't know about yet. These aren't explained by the standard model of particle physics or the lambda CDM model, which is the main cosmology model we use. These strange findings push us to find a more united theory that can connect the laws controlling the huge cosmos with those ruling the tiniest particles. Building on how cosmology connects with particle physics, we need to understand the basic forces of nature. These are the backbone of both the huge cosmos and the world of subatomic particles. These forces are like the universe's rulebook, deciding how everything interacts, from galaxies to quarks. Understanding these forces helps us know everything from how planets move to why matter stays stable. There are 4 known basic forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each plays an important role in how the universe is built and works, affecting interactions at different sizes and energy levels. Gravity is probably the most familiar force, keeps our feet on the ground and controls how planets, stars, and galaxies move. Even though it's everywhere, gravity is the weakest of the 4 forces, but it works across huge distances, holding the universe together. How strong gravity is between 2 objects depends on how heavy they are and how far apart they are. This was described by Isaac Newton's law of universal gravitation. Albert Einstein's theory of general relativity later improved our understanding of gravity, describing it as the bending of space-time around heavy objects. Electromagnetism is the force behind almost everything we experience in daily life above the atomic level. It works between charged particles like protons and electrons. It's the force behind electricity, magnetism, and light. Electromagnetism is much stronger than gravity when looking at particles. It's essential for how atoms are built, how atoms bond together chemically, and how signals move through our bodies. The strong nuclear force, also called the strong interaction, is the strongest of the four forces but only works over very short distances. It ties protons and neutrons together in the center of an atom. Without the strong force, atoms wouldn't exist as they do now. It overcomes the electromagnetic push-away between positively charged protons in the nucleus. This force also holds quarks together to make protons and neutrons, which are the parts of atomic centers. The weak nuclear force, or weak interaction, causes radioactive breakdown and certain types of nuclear reactions like the ones powering the sun. It works over an even shorter distance than the strong force. It's key in processes that change one type of subatomic particle into another, like turning a neutron into a proton, electron, and neutrino. This force plays a big role in the nuclear fusion reactions that power stars and, by extension, in making elements throughout the universe. These basic forces of nature are central to the theories and experiments that connect the hugeness of cosmology with the details of particle physics. Scientists work to develop a unified theory that can explain all four forces in one framework, a goal that has stayed out of reach. The search for such a theory, often called the theory of everything, continues to drive much of the research in physics. Promises to unlock more mysteries of the universe. Let's look at the particles that are considered the very building blocks of matter itself. These particles form the foundation of everything we can see and touch in our world, from the air we breathe to the stars in the night sky. The standard model of particle physics gives us a framework that identifies the smallest pieces of matter. It groups them into quarks, leptons, and the force carrier particles that handle the basic forces. Quarks are incredibly tiny particles that join together to make protons and neutrons, the parts of atomic centers. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Quarks are never found alone in nature because of something called color confinement. They're always stuck together in groups of 2 or 3, making particles called mesons and baryons. Protons are made of 2 up quarks and 1 down quark. Neutrons are made of 2 down quarks and 1 up quark. How quarks behave and interact is controlled by the strong nuclear force, the most powerful of the 4 basic forces. It keeps them locked together inside the nucleus. Leptons are another group of basic particles, with the electron being the most well-known one. Like quarks, there are 6 flavors of leptons: the electron, muon, tau, and their matching neutrinos, electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons don't feel the strong nuclear force. Electrons circle around the nucleus of an atom, playing a big role in chemical reactions and electrical flow. Neutrinos are hard-to-catch particles that barely interact with matter. This makes them incredibly difficult to detect, even though they're made in huge amounts by the sun and other nuclear processes. Besides quarks and leptons, the standard model includes force carrier particles called bosons. These handle the 4 basic forces. Photons carry the electromagnetic force. Gluons handle the strong force. W and Z bosons are responsible for the weak force. And the recently confirmed Higgs boson is connected with the Higgs field, which gives particles their mass. As we continue our journey, we enter the realm of the Big Bang Theory, an important idea that gives a convincing explanation for where the universe came from. This theory is a cornerstone of modern space science and gives us a window into the universe's earliest moments. It suggests that everything we see today, from the smallest particles to the biggest galaxies, came from one incredibly packed and hot point about 13.8 billion years ago. The Big Bang Theory says the universe was once in an extremely hot and dense state that expanded quickly. This expansion isn't like an explosion of stuff moving outward to fill empty space. Instead, it's the expansion of space itself. Think of a balloon with dots on it representing galaxies. As the balloon inflates, the dots move away from each other. This shows how galaxies move apart as the universe expands. Evidence supporting the Big Bang theory is varied and convincing. One key piece of evidence is the cosmic microwave background radiation, CMB, a faint glow that fills the universe. It was discovered accidentally by Arno Penzias and Robert Wilson in 1965. This radiation is the afterglow of the Big Bang, stretched to microwave frequencies by the universe's expansion. Observations of the CMB give us a snapshot of the baby universe, letting scientists learn about its early conditions and what it was made of. Another key piece of evidence comes from watching the redshift of galaxies, showing that the universe is still expanding. This redshift happens because light from distant galaxies is stretched to longer, redder wavelengths as the space between us and the galaxies expands. Edwin Hubble was the first to see this in 1929, giving direct proof that the universe isn't still but active and always expanding. Also, the Big Bang theory explains the relative amounts of the lightest elements in the universe, hydrogen, helium, and lithium, that we see today. These elements were made in the first few minutes after the Big Bang in a process called nucleosynthesis. Their proportions match closely with what the theory predicts. Despite being widely accepted and having strong evidence supporting it, the Big Bang theory has unanswered questions and mysteries. These include what dark matter and dark energy really are. They dominate the universe's total mass energy but remain hard to find. Also, the theory doesn't explain what came before the Big Bang or what caused the initial expansion, leaving room for more theoretical and observational exploration. The Big Bang theory has changed how we understand the universe's origins, structure, and evolution. It paints a picture of a dynamic universe, born from a single state of unimaginable density and heat, evolving over billions of years into the complex cosmos we see today. In the immediate time after the Big Bang, the universe was a hot, dense sea of energy. Conditions were so extreme that matter as we know it, atoms, molecules, and their parts couldn't exist yet. Instead, the universe was filled with a quark-gluon plasma. This is a state where quarks, the building blocks of protons and neutrons, and gluons, the particles responsible for the strong force that binds quarks together, moved freely in an ultra-hot, dense environment. This phase is like a soup of the universe's most basic ingredients, cooking in the aftermath of its explosive birth. As the universe expanded, it started to cool. Within the first microseconds, it cooled enough for quarks to start sticking together, forming protons and neutrons, the centers of future atoms. This period, called the Hadron Epoch, marked the universe's first step toward forming matter as we know it. Further cooling allowed protons and neutrons to begin forming the universe's first nuclei during the nucleosynthesis phase, a few minutes after the Big Bang. Mainly, these were the simplest nuclei: hydrogen, which is a single proton, deuterium, a stable form of hydrogen with one neutron, helium, and tiny amounts of lithium. The exact ratios of these light elements, predicted by the Big Bang nucleosynthesis theory, match closely with what we see in the universe today. This gives strong support for the Big Bang model. However, the universe stayed too hot for electrons to attach to these nuclei to form neutral atoms. It wasn't until about 380,000 years after the Big Bang, during a period called recombination, that the universe had cooled enough for electrons to combine with nuclei, creating the first neutral atoms. This event dramatically changed the universe's structure, allowing light to travel freely through space for the first time. This led to the release of the cosmic microwave background radiation, a snapshot of the infant universe that gives critical evidence for the Big Bang. The formation of the first neutral atoms marked the universe's change from a plasma state to one that could eventually support stars, galaxies, and planets. Gravity began to pull matter together, leading to the formation of gas clouds that would become nurseries for the first stars. These first stars made heavier elements in their cores, adding to the rich chemical variety we see in the universe today. The evidence for the Big Bang Theory not only backs up the idea that the universe came from a single, extremely dense and hot state. It also gives us insights into how the cosmos has moved and changed over billions of years. This evidence is crucial for both the scientific community and the wider public, offering a clear story of cosmic evolution based on observation and analysis. The cosmic microwave background radiation, CMB, stands as a huge pillar of evidence for the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint glow of light that fills the universe, left over from the time shortly after the Big Bang. This radiation is the afterglow of the universe's infancy, cooled to microwave frequencies by the expansion of the universe over billions of years. Measurements of the CMB by satellites like COBE, WMAP, and Planck have given a detailed picture of the early universe. They show slight temperature changes that match with regions of slightly different densities. These changes were the seeds of all future structure, the galaxies, stars, and planets that fill the universe today. The expansion of the universe itself serves as direct evidence for the Big Bang. In the 1920s, Edwin Hubble made the groundbreaking discovery that galaxies are moving away from us in every direction. Their speed is related to their distance from us. This observation, known as Hubble's law, suggests the universe is expanding evenly. This means it was once far smaller, hotter, and denser, just as the Big Bang Theory predicts. The expansion of the universe is a dynamic proof of its explosive origin. The amount of light elements provides another key piece of evidence. The Big Bang Theory predicts the production of hydrogen, helium, and traces of lithium during the first few minutes after the Big Bang in a process called primordial nucleosynthesis. Observations of the relative amounts of these elements in the universe match closely with the predictions made by the Big Bang model. This supports the theory that the universe was once in a hot, dense state good for forming these elements. The large-scale structure of the universe, as seen through how galaxies and galaxy clusters are spread out, supports the Big Bang Theory. Galaxies aren't randomly scattered throughout the universe. Instead, they form a vast web of filaments and voids. This structure fits with the gravitational growth of initially small changes in the density of the early universe predicted by the Big Bang Theory. Continuing on our journey, we look into the concept of quantum fluctuations, a phenomenon deeply rooted in the quantum realm that plays a key role in the fabric of the cosmos. Quantum fluctuations are temporary changes in the amount of energy at a point in space. This is dictated by Werner Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, can't both be measured exactly at the same time. This principle is a cornerstone of quantum mechanics and introduces the concept of built-in uncertainty at the quantum level. In the vacuum of space, what we might think of as empty quantum fluctuations happen on their own. Particles and antiparticles pop into and out of existence. These particles, called virtual particles, exist for an incredibly short time before destroying each other. Despite their brief nature, they have real effects and can influence how other particles behave. For example, quantum fluctuations are believed to cause the slight shifts in the energy levels of electrons in atoms, an effect that's been observed and verified through experiments. Quantum fluctuations aren't just a curious part of quantum mechanics. They're thought to have played a critical role in forming the universe as we know it. During the period of cosmic inflation, a brief period of rapid expansion that happened a fraction of a second after the Big Bang, these quantum fluctuations were stretched to huge scales. This process made the tiny changes in the universe's density bigger, leading to the large-scale structures we see today, like galaxies and galaxy clusters. The patterns printed in the cosmic microwave background radiation are a direct result of these quantum fluctuations, giving us a glimpse into the quantum origins of the universe. At the heart of quantum fluctuations is the Heisenberg uncertainty principle. It says that certain pairs of physical properties, like position and momentum, can't both be known exactly at the same time. This principle suggests that even what we consider a vacuum isn't truly empty. It's actually full of virtual particles popping into and out of existence. These particles are called virtual because they can't be directly seen. They exist temporarily, borrowing energy from the vacuum to appear for a brief moment before destroying each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to creating real particles. One such situation happens near the event horizon of a black hole, a phenomenon called Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole could result in creating particle-antiparticle pairs. One particle falls into the black hole and the other escapes into space. This process effectively leads to creating real particles from the vacuum, with the black hole losing mass over time because of this radiation. Another context where quantum fluctuations lead to particle creation is during the period of cosmic inflation. This is a theory suggesting the universe went through rapid expansion shortly after the Big Bang. During inflation, quantum fluctuations were stretched to huge scales, making their effects bigger. These changes in the density of the early universe served as the seeds for forming all large-scale structures we see today, like galaxies and galaxy clusters. The magnification of quantum fluctuations during inflation means that the virtual particles could freeze into real particles, adding to the matter content of the universe. This process of particle creation from quantum fluctuations shows the connection between quantum mechanics and cosmology. It reveals the quantum foundations of cosmic evolution. It shows how the universe at its largest scales is influenced by things happening at the smallest scales, blurring the lines between the void and the real, between nothingness and existence. Diving deeper into the quantum realm, the role of energy in particle formation is a critical part that bridges the gap between the temporary nature of quantum fluctuations and the real reality of the universe. Energy plays a key role in the birth of particles, acting as the trigger that transforms the potential within quantum fluctuations into the material pieces of the cosmos. This process is rooted in one of the most famous equations in physics, E equals mc squared. This was proposed by Albert Einstein and says that energy, E, and mass, m, can be swapped, with c being the speed of light. This basic principle shows the deep connection between energy and creating particles. It illustrates how changes in the quantum vacuum can give rise to matter. In the vacuum of space, what appears to be empty is actually a bubbling cauldron of energy due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing for the creation of particle-antiparticle pairs. Although these pairs typically destroy each other almost instantly, returning the borrowed energy to the vacuum, under certain conditions they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For instance, in the incredibly high-energy conditions that followed the Big Bang, the universe was a hot, dense soup of energy. As the universe expanded and cooled, some of this energy condensed into particles, following the principles laid out by Einstein's equation. The early universe went through various phases, including the electroweak epoch and the quark epoch. During these times, the basic forces of nature separated and the building blocks of matter formed and came together into the protons and neutrons that make up atomic centers today. Energy not only helps create particles but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion processes in the hearts of stars is responsible for making the heavier elements essential for life, from carbon to iron. This transforming power of energy, from lighting stars to forging elements, highlights its basic role in shaping the cosmos. Moving from the key role of energy in particle formation, we find ourselves at the doorstep of another basic concept we talked about earlier, the Heisenberg uncertainty principle. This principle isn't just a mathematical curiosity. It's a window into the built-in fuzziness of the quantum world and has direct effects on creating particles from seemingly empty space. The uncertainty principle, introduced by Werner Heisenberg in 1927, states that it's impossible to know both the exact position and exact momentum of a particle at the same time. This built-in uncertainty isn't because of imperfect experiments. It's a basic property of the universe at the quantum level. The uncertainty principle is closely related to particle creation, particularly in the context of quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum isn't empty. It's full of virtual particles that continually pop into and out of existence. These particles are called virtual because they exist temporarily, borrowing energy from the vacuum due to the allowances made by the uncertainty principle. The principle permits these changes by allowing a temporary break of energy conservation, with the rule that the borrowed energy must be paid back quickly. This prevents any break from being directly observed. This temporary borrowing of energy makes it possible for particle-antiparticle pairs to form on their own. Although these pairs usually destroy each other almost immediately, returning their borrowed energy to the vacuum, their brief existence is a direct result of the uncertainty built into their positions and momentums. In certain extreme conditions, like near the event horizon of a black hole or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of particle creation from the vacuum, helped by the uncertainty principle, highlights the principle's crucial role in the dynamics of the quantum world and the fabric of the cosmos. In the initial fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with a quark-gluon plasma, a state of matter where quarks, basic particles that later formed protons and neutrons, weren't confined within atomic centers. Instead, they were free in a soup of gluons, particles that handle the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature where quarks could come together to form protons and neutrons, the building blocks of atomic centers. This time, called the Hadron Epoch, happened within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons marked a key moment in the early universe, setting the stage for creating more complex forms of matter. Following the Hadron Epoch, the universe continued to cool, leading to the Lepton Epoch. This lasted from about 1 second to a few minutes after the Big Bang. During this period, leptons, like electrons, were the main form of matter. The universe was still too hot for protons and neutrons to combine into nuclei with these electrons. The most critical event related to particle formation came next: nucleosynthesis, a process that happened within the first few minutes after the Big Bang. During this time, the universe had cooled enough for protons and neutrons to begin combining to form the nuclei of the simplest elements: hydrogen, helium, and trace amounts of lithium and beryllium. This early nucleosynthesis was responsible for creating most of the helium in the universe, alongside the hydrogen that didn't bind into helium nuclei. It's important to note that these weren't yet complete atoms as we think of them today. with electrons circling a nucleus. The universe stayed too hot for electrons to be captured into orbits around nuclei, forming neutral atoms. This formation of neutral atoms, a process called recombination, wouldn't happen until about 380,000 years after the Big Bang. This led to the uncoupling of matter and radiation and the release of the cosmic microwave background radiation, the afterglow of the Big Bang. This gives us a snapshot of the universe at that time. Now let's go further into the fascinating time when the basic forces of nature began to separate and define the evolving cosmos. This story of separation is a cornerstone in understanding the universe's complex pattern, from its newest moments to the richly structured space we see today. Initially, in the universe's first moments, all forces were united in a single force. This was a sign of the extreme conditions of temperature and density that filled the cosmos. As the universe expanded and cooled, this original unity broke apart in a series of symmetry-breaking events. This led to the distinct forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The first to separate was gravity, emerging as a distinct force as the universe cooled from its unimaginably hot and dense state. This separation is thought to have happened just a fraction of a second after the Big Bang, marking the universe's first step toward the complex force interactions that control it now. Gravity's splitting off set the stage for the cosmos's large-scale structure, guiding the formation of galaxies, stars, and planets, shaping the very fabric of the universe. Following gravity's separation, the grand unified force, wrapping up the electromagnetic, strong, and weak nuclear forces, continued in its unified state until the universe cooled more. As the temperature dropped to a critical point, the strong nuclear force, responsible for binding quarks within protons and neutrons and keeping atomic centers intact, separated itself from the electroweak force, a combined form of the electromagnetic and weak nuclear forces. This separation, happening roughly 10 to the power of -36 to 10 to the power of -32 seconds after the Big Bang during the cosmic inflation time, laid the groundwork for forming the universe's first particles. The electroweak force continued to control the universe's energetic landscape until it too went through symmetry breaking. This event, taking place about 10 to the power of -12 seconds after the Big Bang, saw the electroweak force split into the electromagnetic force, handled by photons, and the weak nuclear force, responsible for radioactive decay and nuclear fusion processes in stars. This separation finalized the lineup of basic forces, setting the stage for the universe to cool further, allowing for the formation of more complex particles and, eventually, atoms. The separation of the basic forces during the universe's infancy was a key series of events that enabled the variety of matter and structures seen in the cosmos today. Moving on from the key moments when the basic forces of nature began their gradual separation, we look into the importance of the electroweak epoch, a defining period in the universe's evolution. This epoch represents a critical phase shortly after the Big Bang, during which the electromagnetic and weak nuclear forces, two of the four basic forces, were united as a single force called the electroweak force. The electroweak epoch happened about between 10 to the power of -12 seconds and 10 to the power of -6 seconds after the Big Bang. This was a time when the universe was cooling down from its initially hot and dense state, yet still incredibly energetic and active. The importance of the electroweak epoch lies in its role in shaping the early universe and setting the stage for forming matter as we know it. During this epoch, the universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles, along with the electroweak bosons that handled the unified force. As the universe expanded and cooled, it reached a critical temperature that allowed the electroweak force to go through a symmetry-breaking event. This event led to the separation of the electromagnetic force, handled by photons, from the weak nuclear force, handled by W and Z bosons. This separation was a basic step in the universe's maturation, allowing for a variety of interactions that would eventually lead to forming atoms and, as a result, the structure of the cosmos. The electroweak epoch has deep effects on our understanding of particle physics and the Standard Model. The Higgs mechanism, predicted by the Higgs field's presence, played a crucial role during this epoch. The interaction of particles with the Higgs field gave them mass, a process central to the symmetry-breaking event that separated the electromagnetic and weak nuclear forces. The discovery of the Higgs boson in 2012, a particle associated with the Higgs field, provided a key piece of evidence supporting the theoretical framework describing the electroweak force and its importance. Quarks, the basic parts of matter, are subject to the strong nuclear force, one of the four basic forces that became distinct in the earlier phases of the universe's evolution. This force, also called the strong interaction, is remarkably powerful, but it only reaches over very short distances. In the universe's early moments, it acted as the glue that bound quarks together in groups of 3 to form baryons. These include protons and neutrons, the building blocks of atomic centers. The process began when the universe cooled enough for the strong force to overcome the kinetic energy that had previously kept quarks apart. In this cooler, yet still incredibly hot, environment, quarks started to interact more closely, forming pairs called quark-antiquark pairs and triplets that would evolve into protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. The specific combination of quarks determines the properties of the particle, including its charge. Protons carry a positive charge because of their quark makeup, while neutrons are neutral. This phase of the universe's development wasn't just about forming these particles. It was also about the change from a state where quarks could move freely, a quark-gluon plasma, to a state where they were locked within protons and neutrons. This locking mechanism is crucial for the stability of matter as we know it. Without it, the complex structures that make up the universe, from atoms to galaxies, couldn't exist. The combining of quarks into protons and neutrons set the stage for the next phase of cosmic evolution, the nucleosynthesis era, when the first atomic centers formed. These early steps of matter coming together from the basic forces and particles shaped by the conditions of the early universe are central to our understanding of cosmic history and the very matter that makes up the world around us. As the universe continued to expand and cool after forming protons and neutrons, it reached a temperature good for fusing these particles together. This time, happening roughly 3 minutes after the Big Bang, was when conditions were just right for nuclear forces to overcome the pushing away electromagnetic forces between positively charged protons. This allowed them to come together with neutrons to form the centers of the simplest elements. Mainly, hydrogen nuclei, protons, fused to form helium, along with trace amounts of deuterium, heavy hydrogen, tritium, a radioactive form of hydrogen, and very small quantities of lithium and beryllium. The process of nucleosynthesis is critical for several reasons. First, it set the initial amount of light elements in the universe. The proportions of hydrogen and helium created during this time have been measured in the present universe. They're found to match remarkably with the predictions made by the Big Bang Theory, serving as a key piece of evidence for the theory itself. Second, these early nucleosynthesis events laid the groundwork for forming stars. Stars, through their own cycles of nuclear fusion, would later forge the heavier elements essential for life and the complex structures of the universe. The importance of nucleosynthesis extends beyond just creating atomic centers. It marks the universe's change from a place of simple particles and forces to a complex pattern of matter. It was during this period that the universe took its first steps toward chemical variety, setting the stage for the long cosmic evolution that would eventually lead to forming planets, life, and the vast array of space phenomena that fill the cosmos. On our journey for answers, we arrive at the next key chapter in the universe's early history, the formation of the first atoms. This milestone event, happening around 380,000 years after the Big Bang, marked the universe's cooling to a point where electrons could attach with nuclei to form neutral atoms, a period called recombination. The background for this huge shift was a universe expanding and cooling from its initial state of extreme heat and density, setting the stage for the birth of atomic matter as we know it. As the universe cooled, the protons and neutrons that had formed from quarks began to interact through nuclear fusion, creating the first simple nuclei during the nucleosynthesis phase. This mainly led to forming hydrogen, which is simply a single proton, and helium nuclei, along with trace amounts of deuterium, heavy hydrogen, and lithium. These light elements formed the universe's initial chemical makeup, setting an early stage rich in hydrogen and helium, the simplest and most abundant elements in the cosmos. However, the universe remained too hot for electrons to stay bound to these nuclei. They existed in a state of free electron plasma, scattering photons and keeping the universe cloudy. As the universe continued to expand and cool, it eventually reached a temperature where the energy of the photons was no longer enough to ionize hydrogen. At this point, electrons began to combine with hydrogen and helium nuclei to form the first stable atoms. This recombination process greatly reduced the scattering of photons, allowing the universe to become transparent for the first time. The photons released at this point form the cosmic microwave background radiation, a leftover radiation that provides a snapshot of the universe at the moment of recombination. The formation of the first atoms was a turning point in the cosmic story, paving the way for the universe's change from a hot, dense state to a cooler, structured one capable of supporting complex structures like stars and galaxies. It marked the end of the universe's dark ages, a time before the first stars lit up, and set the stage for the gravitational collapse of matter into the first stars and galaxies. These stars would further enrich the cosmos with heavier elements through stellar nucleosynthesis, seeding the universe with the ingredients necessary for planets and life. Nucleosynthesis, the process by which the natural amounts of chemical elements within stars were formed, played a crucial role in creating the variety of elements that we see in the universe today. Following the formation of the first atoms, the universe was mainly made up of hydrogen and helium, the simplest and most abundant elements. However, the complex and varied world around us, from the air we breathe to the materials that make up Earth and even the parts of our own bodies, requires a much broader range of elements. Nucleosynthesis provided the processes necessary to forge these elements, acting as the cosmic furnace that changed the early simplicity of the early universe into a rich pattern of chemical variety. The process of nucleosynthesis happened in several stages and environments, starting with the Big Bang itself. Big Bang nucleosynthesis, happening within the first minutes of the universe, produced the lightest elements including hydrogen, helium, and trace amounts of lithium and beryllium. However, this process couldn't account for creating heavier elements that are essential for life and the structure of the cosmos. The next phase of nucleosynthesis took place within stars. Stars are the universe's factories for element production, transforming lighter elements into heavier ones through nuclear fusion in their cores. In the life cycle of a star, hydrogen nuclei fuse to form helium in a process called hydrogen burning. As stars age and their cores heat up, they can fuse helium into carbon. In more massive stars, the process continues, forming elements up to iron through successive stages of nuclear burning, like carbon burning, neon burning, oxygen burning, and silicon burning. However, creating elements heavier than iron requires a different set of processes. These elements can't be formed through fusion in stellar cores under normal circumstances because of their energy requirements. Instead, processes like the R process, rapid neutron capture, and the S process, slow neutron capture, come into play. These mainly happen during supernova explosions and in the outer shells of asymptotic giant branch AGB stars. Supernovae, the catastrophic explosions that mark the death of massive stars, provide the necessary conditions for the process. Here, a dense flow of neutrons is absorbed by atomic nuclei, leading to creating many of the heavier elements in the periodic table. The S process happens in the more peaceful environments of AGB stars, where neutrons are captured more slowly, allowing for creating elements like barium and lead. The diverse elements forged by nucleosynthesis are eventually spread throughout the galaxy by stellar winds and supernova explosions, seeding space clouds with the materials needed for the next generation of stars, planets, and eventually life. This cycle of star birth, nucleosynthesis, and death, followed by the reformation of new stellar systems, has enriched the universe with complex chemistry over billions of years. Particle accelerators are sophisticated machines that push charged particles, like protons or electrons, to high speeds and smash them together or against targets. This generates conditions that copy those just after the Big Bang. These groundbreaking tools allow scientists to investigate the basic properties of matter and the forces that control the interactions between particles. By speeding up particles to nearly light speed and then colliding them, particle accelerators let researchers break down atomic parts into their basic pieces, revealing particles and phenomena not observable under normal conditions. How a particle accelerator works involves using electric fields to speed up particles and magnetic fields to steer and focus them along a specified path. This can be circular, as in synchrotrons and storage rings, or straight, as in linear accelerators or LINX. When these high-energy particles collide, they produce a variety of new particles. This allows scientists to study the rules of particle physics in environments of extreme energy densities similar to those that existed just after the Big Bang. There are several types of particle accelerators, each serving different purposes in research and beyond. For instance, the Large Hadron Collider LHC at CERN near Geneva, Switzerland, is the world's largest and most powerful particle accelerator. It's designed to probe deeper into the mysteries of the universe, like the properties of the Higgs boson, dark matter, and other basic questions about the nature of reality. Beyond their basic scientific uses, particle accelerators have practical uses in various fields. In medicine, they're used for cancer treatment through radiation therapy and in producing isotopes for medical diagnostics. In industry, they're used for materials processing and creating semiconductors. In art and archaeology, they're used for analyzing paintings and artifacts without damaging them. The development and operation of particle accelerators are feats of engineering and physics, combining advanced technologies in superconducting magnets, vacuum systems, and particle detection to explore the frontiers of human knowledge. These machines aren't just tools for discovery. They're also catalysts for technological innovation, driving advances in numerous fields and contributing to the technological foundation of society. Particle accelerators have been instrumental in advancing our understanding of the basic aspects of the universe, leading to numerous important discoveries that have shaped modern physics. These machines, by pushing particles to high speeds and making their collisions happen, have allowed scientists to probe the deepest secrets of the universe. This has revealed the existence of particles and forces that make up the fabric of everything around us. One of the most groundbreaking discoveries made with the help of particle accelerators was identifying the Higgs boson. In 2012, scientists at CERN's Large Hadron Collider, LHC, announced they had detected a particle consistent with the Higgs boson, often called the God particle. This particle, predicted by the Standard Model of particle physics, is basic to understanding why other particles have mass. The discovery of the Higgs boson was a huge moment in particle physics, confirming a key pillar of the Standard Model and contributing to the Nobel Prize in Physics for François Englert and Peter Higgs in 2013. Particle accelerators have also been key in confirming the existence of quarks, the building blocks of protons and neutrons. In the late 1960s and early 1970s, experiments done at the Stanford Linear Accelerator Center, SLAC, provided the first direct evidence of quarks. This supported the quark model proposed by physicists Murray Gell-Mann and George Zweig in the 1960s. This was a big step forward in our understanding of the structure of matter, establishing quarks as basic parts of matter. Furthermore, accelerators have made it easier to study antimatter particles that are identical to matter particles but with opposite charge. Experiments at CERN and other facilities have allowed physicists to create, trap, and study antimatter particles like antihydrogen. These studies are crucial for testing the basic symmetries of the universe and for understanding why the universe is made mainly of matter, despite the Big Bang theory predicting equal amounts of matter and antimatter. Particle accelerators have also enabled the discovery of many subatomic particles, including W and Z bosons, which handle the weak nuclear force responsible for radioactive decay. The discovery of these particles in the 1980s at CERN provided critical proof of the electroweak theory, which unifies the electromagnetic and weak forces, one of the key achievements in efforts to develop a unified theory of basic forces. Beyond basic discoveries, particle accelerators have contributed to advancements in medical treatments, like cancer therapy through particle beams, and in developing technologies like the World Wide Web. The web was initially created at CERN to make information sharing among scientists easier. Now, how do these experiments in particle physics validate theoretical predictions? The interplay between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behaviors of particles and the forces that control their interactions. These models often make precise predictions about the outcomes of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle accelerators. These machines speed up particles to high energies and then collide them, creating conditions that allow for observing phenomena that aren't accessible under normal circumstances. The detectors surrounding the collision points capture and record the particles produced in these collisions. Sophisticated data analysis techniques are used to interpret the results. A big aspect of validating theoretical predictions is the ability to reproduce experimental results. In particle physics, this often means that multiple experiments, sometimes at different facilities around the world, must observe the same phenomena under similar conditions. This replication of results adds credibility to the findings and helps confirm that they aren't statistical oddities or artifacts of the experimental setup. The Standard Model of particle physics is a theory that describes 3 of the 4 known basic forces in the universe: the electromagnetic, weak, and strong nuclear forces, and classifies all known elementary particles. It's a cornerstone of modern physics and represents the best understanding scientists have of how the basic parts of the universe behave and interact. The model has been developed over several decades, starting in the mid-20th century, through the collaborative efforts of physicists around the world. At its core, the Standard Model is built on the foundation of quantum mechanics and special relativity, bringing both into a unified framework called quantum field theory. The model groups elementary particles into 2 main groups: fermions and bosons. Fermions are the building blocks of matter, divided into quarks and leptons. This includes particles like electrons and the quarks that make up protons and neutrons. Bosons are force carrier particles that handle the basic forces. For instance, photons carry the electromagnetic force, while gluons are responsible for the strong force. A major triumph of the Standard Model was the prediction and later discovery of the Higgs boson, a particle that provides mass to other particles through the Higgs mechanism. This discovery at the Large Hadron Collider in 2012 filled a crucial gap in the model and was hailed as one of the most significant achievements in physics. It confirmed the existence of the Higgs field and its associated particle. Despite its successes, the Standard Model isn't complete. It doesn't include the fourth basic force, gravity, described by general relativity. It also doesn't account for dark matter and dark energy, which appear to make up most of the universe's mass-energy content. Additionally, the model's inability to include the gravitational force or predict the masses of elementary particles suggests that it's part of a more comprehensive theory yet to be discovered. While the Standard Model of particle physics stands as a remarkably successful theoretical framework, it also has its limitations. These mark areas where our current understanding of the universe is incomplete. These limitations not only highlight the boundaries of the model's usefulness, but also point toward new physics beyond what we currently know, guiding researchers in their quest to uncover a more comprehensive theory of the basic forces and particles. One of the most significant limitations of the Standard Model is its inability to include gravity. Gravity, described by Einstein's theory of general relativity, is a basic force that controls the structure and dynamics of the cosmos on the largest scales, from the orbits of planets to the evolution of galaxies and the universe itself. However, the Standard Model is based on the framework of quantum field theory, which doesn't naturally include gravity. This disagreement between the theories of the very large, general relativity, and the very small, quantum mechanics, remains one of the most deep challenges in physics. Another limitation is the Standard Model silence on the nature of dark matter and dark energy. Observations of the universe suggest that about 85% of its matter content is dark matter. It doesn't give off, take in, or bounce back light and is detectable only through its gravitational effects. Dark energy, contributing to about 68% of the total energy content of the universe, is thought to be responsible for its speeding up expansion. The Standard Model, however, doesn't predict the existence of dark matter particles. It also doesn't account for the properties of dark energy, leaving a big portion of the universe unexplained. The Standard Model also can't explain the matter-antimatter imbalance observed in the universe. According to the model, the Big Bang should have produced equal amounts of matter and antimatter, which would destroy each other, leaving behind a universe filled with radiation. However, the observable universe is dominated by matter, suggesting that processes not accounted for in the Standard Model must have given matter an edge over antimatter. The Standard Model doesn't provide a satisfactory explanation for the masses of neutrinos. Initially, the model assumed that neutrinos were massless, but experiments have shown they have a small mass. This discovery has required revisions to the model, but has also opened up new questions about the origins of neutrino mass and their role in the universe. The Standard Model is a patchwork of particles and forces without a unifying principle that could explain why this particular set of particles and forces exists. The search for a theory of everything that would unify all basic forces, including gravity, and offer a more fundamental understanding of the particles themselves remains a major goal of theoretical physics. Dark matter and dark energy are two of the most deep mysteries in modern cosmology. They represent parts of the universe that are invisible and can't be detected by traditional means. But their presence is figured out from their gravitational effects and the impact on the universe's expansion. Together, They make up about 95% of the total mass energy content of the universe. Dark matter accounts for about 27% and dark energy for about 68%. This leaves ordinary matter, everything we can see and interact with, making up just a small fraction. Dark matter is a form of matter that doesn't give off, take in, or bounce back light, making it completely invisible to electromagnetic radiation. This makes it extremely difficult to detect directly. Its existence was first suggested in the 1930s by Swiss astronomer Fritz Zwicky. He observed that galaxies within clusters were moving at speeds that implied the presence of much more mass than could be accounted for by the visible matter alone. Since then, further evidence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation has supported the existence of dark matter. Despite being invisible, dark matter exerts gravitational forces, influencing the structure and formation of galaxies and galaxy clusters. It acts as a cosmic framework around which visible matter gathers and forms into the large-scale structures observed in the universe. Dark energy, on the other hand, is a mysterious force that's driving the speeded-up expansion of the universe. The discovery of dark energy in the late 1990s was a big surprise to astronomers who had expected that the universe's expansion might be slowing down due to the gravitational pull of its contents. Instead, observations of distant supernovae revealed that galaxies are moving away from each other at a speeding up rate. Dark energy is thought to be a property of space itself, evenly spread throughout the universe and not diluting as space expands. Its nature is even less understood than that of dark matter. It poses a basic challenge to our understanding of the laws of physics, as it doesn't fit neatly into the standard model of particle physics or the theory of general relativity. Dark matter, which makes up about 27% of the universe, interacts with ordinary matter through gravity. It doesn't give off, take in, or bounce back light, making it invisible and detectable only through its gravitational effects. Dark matter's presence is figured out from its gravitational pull on galaxies and galaxy clusters, influencing their rotation rates and how they're spread out. This invisible matter acts as a cosmic framework, providing the gravitational structure necessary for galaxies to form and cluster together. During the early universe, dark matter's gravitational pull helped to make bigger the slight irregularities left by quantum fluctuations, leading to forming large-scale structures like galaxies and clusters of galaxies. These structures created the potential wells within which ordinary matter could gather and cool, leading to star formation and the later making of heavier elements through nucleosynthesis in stars. Dark energy, on the other hand, accounts for about 68% of the universe and is thought to be responsible for its speeded-up expansion. Unlike dark matter, dark energy doesn't cluster, but is evenly spread across space, exerting a pushing-away force that works against gravity. The exact nature of dark energy remains one of the biggest mysteries in physics. But its effect on the universe's expansion rate has critical effects for particle formation and the evolution of the cosmos. The speeded-up expansion affects the density and temperature of the universe over time, influencing the rate at which structures form and evolve. This expansion impacts the cooling of the universe and the regions where particles can come together to form atoms, molecules, and eventually, the stars and galaxies. Supersymmetry, or SUSY, is a leading idea in particle physics that suggests every known particle has a heavier partner we haven't yet discovered. In the standard model, fermions make up matter and bosons carry forces. Supersymmetry pairs them together, proposing superpartners like the squark for quarks and the selectron for electrons. These particles could help solve major mysteries, starting with the hierarchy problem, the question of why gravity is so much weaker than the other forces, and why the Higgs boson's mass is so stable. SUSY naturally protects the Higgs from becoming far heavier than we observe. Another major reason scientists are excited about supersymmetry is dark matter. The lightest supersymmetric particle, if it exists, would be stable, invisible, and weakly interacting, exactly the kind of particle that could account for the missing mass shaping galaxies across the universe. Yet, despite its promise, no experiment has confirmed SUSY. Even the powerful Large Hadron Collider has not found any of these partner particles, pushing the search to higher energies and leaving the theory unproven for now. Supersymmetry is just one of several ideas that try to go beyond the standard model. String theory, for instance, treats particles not as points but as tiny vibrating strings whose different vibrations create different particles. It also predicts extraspatial dimensions and offers a possible path to unifying all forces, including gravity. Other theories propose hidden dimensions where gravity might spread out, which could explain why it seems so weak compared to other forces we observe. Grand unified theories aim to merge the electromagnetic, weak, and strong forces into one, predicting new particles that could change one type of particle into another. These theories are elegant and ambitious, but like supersymmetry, they still lack direct experimental proof. Gravity itself plays a unique role in shaping the particles and structures of the universe. Though weak on small scales, it becomes the dominant force across cosmic distances. Under gravity's pull, giant clouds of gas collapse into stars, where nuclear fusion creates the heavier elements essential for planets and life. Near black holes, gravity becomes so intense that space itself bends dramatically, and quantum theory predicts that particles may constantly form and vanish at the edge of the event horizon. A reminder that gravity and quantum physics are deeply connected in ways we still struggle to understand. On the largest scales, gravity sculpts the cosmic web, clusters of galaxies, and the vast empty spaces between them, defining where matter can gather to form stars and worlds. To understand how all of this began, scientists look back to the moments immediately after the Big Bang. According to the theory of inflation, the young universe expanded faster than the speed of light for a tiny fraction of a second. This sudden balloon-like growth solved long-standing puzzles. One was the horizon problem. Regions of space far apart today should never have had time to exchange heat or information, yet they show nearly the same temperature. Inflation explains that these regions were once close together and able to reach thermal balance before being flung across the cosmos. Inflation also smooths out any noticeable curvature of space, which explains why the universe appears so flat. Perhaps most importantly, it stretched tiny quantum fluctuations into the seeds of galaxies we see today. Those tiny variations became the structure of the universe itself. Stars, planets, and everything we know. We see strong support for inflation in the cosmic microwave background, the faint radiation left over from the Big Bang. Its temperature is almost perfectly uniform everywhere we look, just as inflation predicts. The tiny irregularities, mapped with incredible precision by satellites like COBE, WMAP, and Planck, are the signatures of those early quantum fluctuations that grew into galaxies. Antimatter is a basic concept in physics, mirroring the properties of matter but with opposite charges. For every type of particle that makes up matter, there exists a corresponding antiparticle that makes up antimatter. These antiparticles have the same mass as their matter counterparts but have opposite electric charge and other quantum numbers. The most familiar examples include the positron, the antiparticle of the electron, which carries a positive charge, and the antiproton, which has the same mass as a proton but a negative charge. The existence of antimatter was first predicted by British physicist Paul Dirac in 1928, based on his work extending the equations of quantum mechanics to bring in the theory of special relativity. Dirac's equations suggested the presence of particles that had the same mass as electrons but opposite charge. This prediction was confirmed in 1932 with the discovery of the positron by Carl Anderson. This discovery was groundbreaking, as it provided the first evidence of antimatter and validated Dirac's theoretical framework. When a particle of matter meets its corresponding antiparticle, the two destroy each other in a burst of energy, typically producing gamma rays. This process of destruction demonstrates the equivalence of mass and energy, as described by Einstein's E=mc² equation. It's a basic aspect of antimatter's interaction with matter. Antimatter isn't just a theoretical curiosity, it has practical uses and effects. In medicine, for example, positron emission tomography, PET scans rely on detecting gamma rays from positron destruction to create detailed images of the body. Furthermore, understanding antimatter is crucial for advancing our knowledge of the universe. Cosmologists study antimatter to address basic questions about the Big Bang and why the observable universe appears to be made almost entirely of matter, despite theories predicting equal amounts of matter and antimatter were produced in the universe's early moments. The investigation of antimatter also pushes the boundaries of particle physics, challenging scientists to create, trap, and study antiparticles in laboratory conditions. Experiments with antihydrogen atoms, for instance, aim to compare the properties of hydrogen and antihydrogen to test the basic symmetries of nature. These studies could reveal new physics beyond the standard model, offering insights into the forces and particles that shape our universe. Now let's talk a bit about CP violation and how it relates to matter-antimatter imbalance. CP violation refers to a basic phenomenon in particle physics where the combined operation of charge conjugation, C, and parity inversion, P, is not conserved. In simpler terms, it means that certain processes involving the change of particles into their corresponding antiparticles don't happen in the same way when the charges and spatial orientations are reversed. CP violation is significant in the context of understanding the matter-antimatter imbalance in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts during particle-antiparticle creation processes. However, if all physical processes respected CP symmetry perfectly, matter and antimatter would have destroyed each other completely, leaving behind a universe empty of matter. The observed matter-antimatter imbalance suggests that there must be processes where CP symmetry is violated, favoring the production of matter over antimatter. This violation of CP symmetry allows for subtle differences in the behavior of particles and antiparticles, leading to a slight excess of matter that ultimately gave rise to the structures we see in the universe today. CP violation has been experimentally observed in certain rare breakdowns of elementary particles, like neutral kaons and B mesons. These experiments have provided crucial insights into the mechanisms responsible for generating the matter-antimatter imbalance in the early universe. However, the exact origin of CP violation and its connection to the observed matter-antimatter imbalance remain active areas of research in particle physics. Can we truly understand the origin of the universe? This question has fascinated scientists, philosophers, and religious thinkers alike for centuries. As we dig into the depths of cosmology and particle physics, we uncover glimpses of the cosmic drama that unfolded billions of years ago. Yet, despite our best efforts, there remains a veil of mystery covering the ultimate beginning of the cosmos. Theories like the Big Bang provide a framework for understanding the evolution of the universe from its earliest moments. But when we look back to the very instant of creation, we meet a realm where the laws of physics break down and our normal understanding fails. It's a realm of extreme temperatures, densities, and energies, where the fabric of space-time itself goes through deep transformations. In our quest to understand the origin of the universe, we face the limits of human thinking and the boundaries of scientific inquiry. Can we ever hope to unravel the mysteries of existence with our limited minds and methods based on observation? Or are there realms of knowledge that lie beyond the reach of human understanding? Some argue that the pursuit of understanding is a built-in aspect of being human, driving us to explore, question, and seek answers to the deepest mysteries of existence. Others argue that there are limits to what we can know, and that some aspects of reality may forever escape our grasp. How does the concept of nothing fit into modern physics? It's a question that challenges our basic understanding of reality. In the realm of modern physics, nothing isn't simply an absence of matter or energy. Instead, it's a complex and active landscape controlled by the laws of quantum mechanics. In quantum physics, the vacuum of space is far from empty. It's teeming with virtual particles suddenly popping in and out of existence, borrowing energy from the vacuum for brief moments before destroying each other. This phenomenon, known as vacuum fluctuations, suggests that even in the absence of particles, the fabric of spacetime is bubbling with activity. Moreover, the concept of nothing is connected with the mysteries of the universe's origin. The Big Bang Theory says that the universe emerged from a singularity, a point of infinite density and temperature. But what came before the Big Bang? Was there truly nothing before the universe began its expansion? Or are there realms of existence beyond our current understanding? Research in particle physics has far-reaching effects that extend beyond the confines of the laboratory, offering numerous benefits to society. While the subject matter might seem abstract, the advancements made in particle physics have yielded real outcomes that impact our daily lives. One significant contribution of particle physics research is its role in medical imaging and treatment. Technologies like PET, positron emission tomography, and MRI, magnetic resonance imaging, have their roots in particle physics research. These imaging techniques are crucial for diagnosing medical conditions and guiding treatment plans, improving healthcare outcomes for millions of people worldwide. Additionally, particle physics has paved the way for advancements in radiation therapy for cancer treatment. Techniques like proton therapy, which uses beams of protons to precisely target tumors while minimizing damage to surrounding healthy tissues, have emerged from particle physics research. These therapies offer more effective and less invasive treatment options for cancer patients. Research in particle physics has contributed to developing innovative materials and technologies. For example, the World Wide Web, invented at CERN to make communication among researchers easier, has transformed the way information is accessed and shared globally. Furthermore, advancements in particle detector technologies have led to creating more sensitive detectors used in security screening, environmental monitoring, and even archaeological exploration. The pursuit of basic knowledge in particle physics often drives advancements in other scientific fields. Collaborations between physicists, engineers, and mathematicians foster research across different disciplines that fuels innovation across various fields. Future discoveries in particle physics hold the promise of revolutionizing various aspects of our daily lives. While some of these advancements may seem distant or abstract, their potential impact on society could be deep. One area where future discoveries could have a significant impact is in energy production and storage. Breakthroughs in particle physics could lead to developing more efficient and sustainable energy sources, helping to address pressing concerns like climate change and energy security. For example, advancements in fusion energy research, inspired by the study of plasma physics in particle accelerators, could one day provide a clean and virtually limitless source of power. Discoveries in particle physics may lead to advancements in technology and computing. The development of quantum computing, which draws heavily from the principles of quantum mechanics explored in particle physics, could revolutionize fields like cryptography, drug discovery, and artificial intelligence. Quantum computers have the potential to solve complex problems exponentially faster than classical computers, opening up new possibilities for scientific research and innovation. Particle physics research, while offering immense potential for scientific advancement, also raises several ethical considerations that deserve careful examination. One such consideration is the allocation of resources. Particle physics experiments often require substantial financial investments and access to sophisticated technology. Critics argue that these resources could be better used to address pressing societal issues, like poverty, healthcare, and education. However, supporters argue that investing in basic research can lead to unforeseen technological breakthroughs and long-term societal benefits. Another ethical concern is the safety of particle physics experiments, particularly those involving high-energy particle accelerators. While the likelihood of catastrophic events occurring as a result of these experiments is extremely low, some worry about the potential risks, like the creation of micro-black holes or the release of dangerous radiation. Researchers and regulatory bodies must carefully assess and reduce these risks to ensure the safety of both experimenters and the public. There are ethical considerations surrounding the sharing of knowledge and the potential misuse of scientific discoveries. Particle physics research often yields valuable insights into the basic workings of the universe, which can have wide-ranging effects for technology, medicine, and other fields. However, there's a risk that this knowledge could be weaponized or exploited for harmful purposes. Scientists and policymakers must consider how to balance the benefits of scientific progress with the need to prevent misuse and ensure responsible management of knowledge. Additionally, there are ethical questions related to international collaboration and distribution of research findings in particle physics. Collaborative efforts among scientists from different countries are essential for advancing knowledge in this field. However, issues like intellectual property rights, data sharing, and fair access to research opportunities can arise, particularly in cases where resources are limited or differences exist between nations. Ensuring fair and transparent collaboration is essential for upholding the principles of scientific integrity and promoting global progress. While particle physics research holds tremendous promise for scientific discovery and technological innovation, it also presents complex ethical challenges that must be addressed thoughtfully and responsibly. By considering these ethical considerations and engaging in open dialogue, scientists, policymakers, and society as a whole can work together to navigate the ethical complexities of particle physics research and maximize its potential benefits for humanity. As we end our journey in thinking about the emergence of particles from what appears to be nothingness, we face deep philosophical questions that go beyond the boundaries of observational science. Perhaps, in the cosmic symphony of creation, there lies a deeper truth beyond the grasp of our current understanding, a truth that speaks to the connectedness of all existence and the infinite potential built into the fabric of reality. Could it be that particles arise not from a void of nothingness, but from the boundless reservoir of possibility that fills the cosmos? Ultimately, the question of how particles form from nothing invites us to think about our place in the vast expanse of the universe and to embrace the wonder and mystery that surrounds us. It challenges us to expand our minds beyond the limits of normal thinking and to embrace the boundless possibilities that lie at the heart of existence.